All right, welcome everybody. We are running down on time. We're going to start a new unit today, and our new unit is going to be on pesticides. And this one's a pretty quick one. We may finish it today. This is the last unit I intend to cover, so if we do finish it today, that means I'm not going to be starting any new units next week. So that would mean no class on Tuesday. We actually did very well. Like with the strike, I was worried because we lost 6 classes as a result of the strike. But then, of course, they changed the schedule, which I think gave us 1 back. And there's a few other things that were different this year, which, like the midterm, we didn't have a midterm and things like that. So I managed to save some time, and we're kind of finishing right on target, which I'm very happy about. The unit assignment for this last unit opens today. Well, I think it opened actually a couple of days ago. We should complete that today, but the due date for this is going to be the only exception out of all of the ones this year. I've set the due date for the current pesticides unit to be next Wednesday at midnight, or a minute before midnight, just because that's the last day of class and we can't give you work that's due after the last day of class. So that means you have 6 days for that instead of 7, although technically you had 8 because I did open it a couple days ago, but we never covered it in class, so you know what I mean. You guys got that figured out. I got an important email from Zach. Yes, I have a lot of emails that are, I feel like I'm answering a lot of emails, but they're building up faster than I'm answering them. So if you haven't heard from me, and if you emailed me more than like a day ago, please send me another email because it's possible I missed it. There are 359 people in this class right now, and I'm getting just many messages about many different things. And the other thing that happens is sometimes those emails are back and forths a few times. And so if you could give me context too about exactly what your particular situation is. And this is one of 3 classes I'm teaching right now, and everything's like crunching all in these last 2 weeks. Plus honors presentations in chemistry are Monday, Tuesday, Wednesday next week, and I have 2 honors students. So I apologize if I haven't been very timely getting back to everybody's emails, but I'm doing my best. I guess that's what I can say. One other piece of information I wanted to send your way is if you log into our Acorn page and go to the top of the page, there's something new there. It says optional unit assignment. And what this is an opportunity for anybody who missed an assignment or did poorly on one of the unit assignments or just would like to upgrade one of their unit assignments for any reason. So I know a lot of people have been emailing me, oh, I missed this assignment, I missed that one, can you open it again? And I kept saying, you know, hang tight, I got a solution in the works. Well, the solution in the works is now deployed. So I just wanted to let you know that that's open. And so what the idea is for this new unit assignment is what you have to do is pick the unit that you want replaced, and you have to come up with a new either set of multiple choice questions based on that unit that don't repeat the questions that are already in the unit assignment, or the second option was to like create like a bit of a study guide for that particular unit. So if you were going to make a study guide for yourself for studying, I know some people like to do that when they study, just put one together and upload it. They all have to go up as Word documents, and there's a Dropbox on there. And the deadline for that is also going to be next Wednesday at midnight. And so this shouldn't take like a ton of time or work, but if that's of interest to you and you would like to replace one of your missed assignments or bad grade assignments or whatever, this is should be down your alley. Someone is saying that they don't have their grades for assignment 1. I think those were posted like a long time ago. Like, I think those were posted within a week of the due date of assignment 1. So they're on Acorn under grades. If you haven't seen your Unit 1 assignment grade yet, or if it's not there, on Acorn for any reason. The only reason I can imagine would be if you didn't do it. But if that's the case, send me an email and I'll double check. As I said, there's a lot of people in the class, so it wouldn't be unheard of for 1 or 2 people to slip through the cracks. Zach says, he wanted to know if we had to physically be seen in the video or if our voices were sufficient as appearance. So those assignments are due today, by the way, assignment 2. And I think I said later today, like end of day. And one of the requirements is that everybody whose name is attached to the video has to make an appearance in the video. The purpose of this rule is so that somebody doesn't realize, like today, oh God, I never thought of that assignment yet. Can you just throw my name onto your assignment, group X, Y, Z, you know, and then just someone get credit for not participating. So if you have to physically appear in the video to get credit for being in the video. So as long as, if someone's not physically seen in the video, but it's obvious that it's their voice, that's fine too. Okay. I notice some people too, like, have videos of themselves, but their like faces are like not in it, and like that's fine too. Like as long as the number of bodies I can count equals the number of names that are attached. Like I'm not running facial recognition software or anything like that. So everyone should be okay. Now that said, I think we are kind of like good, right? Final exam is going to open Wednesday next week. And it's going to be 100 questions. They're all going to be multiple choice, and it's all going to be through Acorn. Acorn is going to randomize from a large test bank so everyone gets their own personal exam copy. It's going to more or less equally span all units. Now, some units are longer than other units, so there'll be more emphasis on some than others. But I'd say the emphasis on each unit should more or less match the emphasis based on the number of questions on the unit assignments. So the longer chapters have more questions on the unit assignments, et cetera, et cetera. All of the unit assignment questions, so by the way, that bonus replace a grade option, if you can't actually access the old, like all of the unit assignments that have already passed, you can't go into them anymore and look at them and see the questions anymore. However, all of those questions are copied in the slides. So if you want to know how many unit assignment questions there were for a given unit assignment, go to the slides and just go to the end and see what number the last question was. Or they're all in the lectures as well. So if you're going through the lectures, you can tell how many unit assignment questions there are per lecture. So that's 2 ways you can find out how many assignments there are without actually physically going into the previous assignments. So I advise you, take that up. Remember, those unit assignments are worth a lot. Like 50% of your grade, I think, is based on the unit assignments. So you don't want to drop points there if you don't have to. All right. Our new unit is on pesticides. And with topics like this, I find it's hard to, completely describe an entire topic in one short unit in a course like this. You could have a whole, whole degree based on just this one topic. So rather than like, a complete view of all pesticides, it's almost more going to be like topics in pesticides. I'm going to talk about a few specific ones, maybe some more notable ones, some ones that are in the news, some that are like more maybe historically important, and yeah, go from there. All right, so pesticides are basically chemicals that are used to kill something. And the idea with a successful pesticide is it does a really good job of killing some target organism, but doesn't kill non-target organisms. And so it can be used to kill plants, which would be an herbicide, kill weeds, for example. It could be an insecticide to kill bugs, fungicide to kill mold or whatever, or kill a whole bunch of other things. So like kill mollusks, kill rodents, all these different things to kill different things. Killing rodents, by the way, I actually have a composter outside my house that there's a little hole in the bottom that rats are going in. So I'm in the process of dealing with that situation right now. Not by killing them. I'm just going to lock them out. They can go somewhere else. Hopefully not in my house. So pesticides have been used for a long time. People have been bothered by various organisms since time has began. Sulfur was one of the earliest chemicals used. Sulfur is just a pure element. It's a yellow, pure substance. It can be mined in certain places. Sulfur, by the way, if you melt it, makes this kind of dark orangish liquid that is called brimstone. So, you know, they talk about hell smelling like sulfur and fire and brimstone. Brimstone is sulfur, if you're wondering what that ever was. This is a picture of North Vancouver, a gigantic pile of sulfur that in this case was extracted from natural gas, mostly from Alberta, and shipped there, and then it goes onto container ships and sent overseas for various use. It was used about, you know, there's evidence that it's being used 4,500 years ago as a pesticide. Another view of this, you can see how like huge this pile is compared to like this little house here and things like that. I wonder what that would be like to play in, you know, like a giant sandbox full of just sulfur. I don't know, might be fun. If you're ever in Vancouver and you're going around Stanley Park, around the seawall, keep an eye open for this. There's like one part where you can look across the water and see it. Heavy metals, we know heavy metals can be pretty toxic to us and to organisms as well. People used to use these to kill insects or kill whatever. Things like arsenic, mercury, and lead, which are all heavy metals. Heavy metals just means they're metals that are kind of far down on the periodic table, so they have a considerable weight per atom. These, by the way, like they may be effective in killing certain organisms, like insects or whatever. The problem is with these is they're also good at killing us. So this would be an example of like not a great pesticide because it has too much risk for non-target organisms. Okay, so apparently arsenic-based pesticides were used a lot in the Annapolis Valley to kill pests of the apple tree. So apparently a lot of farmland around here is contaminated with higher than normal levels of arsenic as a result of years of use of arsenic pesticides. The problem with arsenic too is that it's persistent. It'll stay in the soil for a long time, where I guess an ideal pesticide, you'd spray it, it would do its job, and then it would decompose and not have any sort of non-target effects. Which was not used historically as a pesticide? The answer here is polonium. Polonium would definitely kill pests, but it's radioactive. It would kill all kinds of things and hang around a long time. All right, we talked about this. We're going kind of right back to one of our first topics when we talked about the difference between organic food and, I guess, I don't know, non-organic, regular food, conventionally grown crops, sometimes it's called. And one of the big, I guess, big things people believe about organic food, which is not true, is that organic foods are grown without pesticides. And that's actually not true. They definitely use pesticides. It's just that the pesticides that are used in organic foods have to come from a natural source and not be synthetically produced. And we talked quite a bit at length early on in the course about the difference between artificial and natural sources of things. We're going to take a look at some pesticides that are used in organic farming and some that are used in conventional farming as well. These would be examples of herbicides because the purpose of most of these pesticides is to kill weeds, non-target plants. So the World Health Organization has created a scale to rate the hazard associated with various types of pesticides, and it's based on LD50 for the rat. They consider humans and rats to be kind of similar because we have, I guess, similar diets. We both eat a wide variety of things, which is why rats typically thrive where humans thrive. And LD50 we know is a measure of acute toxicity. that something with a low LD50 will poison you very easily. Something with a high LD50 is relatively non-toxic. So the group 1A ones, we would say if it's got LD50s less than 5 milligrams per kilograms body weight, it's extremely hazardous. And then you can see the different brackets for highly, moderately, slightly, unlikely to present an acute hazard. So which pesticides can be used in organic farming has nothing to do with this table. It's not like, oh, well, all the safe ones we can use in organic farming and the non-safe ones we can use. No, it's based on their source, not on their risk or hazard. And we'll take a look at some of that. Organic agriculture only allows pesticides to be used that are what? And the answer here is naturally derived. Okay? It's not based on toxicity or anything like that. This is a common misconception, this one. No pesticides are allowed in organic farming. And we're going to look into that in a little more detail today. So what pesticides are you allowed to use in organic farming? Well, this is actually dictated by the federal government. The Government of Canada General Standards Board has created this list that you can go and you can download. And it's a list of all of the different substances that you can use in organic farming and still legally call your food organic food in Canada. And this list might be slightly different in different countries. And so it goes through a whole list of things here. You can see various things. Some of these are chemicals. Some of these are like physical things. So you're allowed to use plastic for row covers, for example, which is, I mean, I guess plastic is technically a chemical, but it's not like a spray or something like that that you put on your food. And the first one I've circled there is a chemical called rotenone. Rotenone. And so this is a pesticide. It's used, I believe, to kill insects. And this is something that you could use in your organic farm if you want to start one up. So rotenone is a complex molecular structure. This is the structure of the molecule, which probably for most people in the class doesn't mean a whole lot. It just looks big and complicated. There may be a few chem students in there, though, that might see some interesting features of these structures. One thing that we do in organic chem, one of the first things we do is learn how to look at a molecule like this and recognize the different components of the molecule to see what types of what we call functional groups are present in the molecule, which gives you an idea the kind of reactions it can do. But this is a natural compound. It's produced from the seeds of the jicama plant, which looks like this. So you can collect the seeds and crush them up and extract them and get an extract of this stuff, and you can spray that on your crops all you like. So you can look up this one. This has been studied in terms of its risk profile. And it turns out this falls into the World Health Organization class of moderately hazardous. That means its LD50 for oral consumption is somewhere between 50 and 2,000 milligrams per kilogram body weight. So it's not like it's, you know, no risk at all, but I'd say it's pretty moderate. One thing I will say is in Canada, basically every member of the 1A class has been banned in Canada. So you don't find any pesticides in use in Canada that would fall under the extremely hazardous category. That would probably be stuff like, maybe like the arsenic we looked at earlier, or the polonium would definitely fall into 1A. It'd be extremely hazardous. Most of them are in the 2B or lower. Another one that's on this list is pyrethrum. Pyrethrum is a chemical that has this structure. R, by the way, in organic chemistry, when you have R hanging off a molecule, what R means is it's like some group that can change. So it might be like 5 different molecules with 5 different R groups. They're all the same except for what that R looks like. So sometimes we use this to abbreviate a part of a molecule that can be maybe more than one different thing. Pyrethrins are naturally occurring molecules that are extracted from chrysanthemum flowers. And pyrethrins are toxic, very toxic to insects, which is why the plant produces the chemical, keeps the insects from devouring the plant. And it's like partly toxic to human beings. It falls into the moderately hazardous category. There's actually a story about pyrethrins. I don't know how true this is because it's like from like ancient Greece or ancient Rome, where apparently there was a field that was full of chrysanthemum flowers, and it was like a meadow, you know, and there was a whole bunch of bees that would pollinate the plants, and they had beehives all over the place. And what the bees would do, the locals knew not to eat the honey from the beehives, because what the bees would do when they collect pollen from these plants, not pollen, they collect, maybe they do eat pollen too, but they collect nectar mostly to make the honey. They would also take pyrethrins with it. It would be in the nectar, and the honey was actually toxic to people. It would make people sick because it had too much of this compound naturally from the honey, from the bees. And I guess the bees were tolerant enough to it that it didn't kill the bees off. I guess bees would have to be a little more hardy when it comes to certain pesticides than other insects, since they go from flower to flower to flower. And apparently the story was there was like an advancing army, and the defending army knew they were like way outnumbered and were going to lose. So what they actually did is they retreated, and then the other army pursued them. And they retreated just at the right time because they knew when night hit, they would be in this meadow and they'd be looking for something to eat. So apparently what they did is they went and they hid, and then this army set up camp, and they went out and they found all these beehives and they broke them all open. Everyone was eating the honey and the beeswax, and people eat that too. And then they all got sick, and then the other army just went back in and like killed them all while they were like groaning and on their side. So I feel like I need to look that up. That's an only a half remembered story there. Anyway, pyrethrin is moderately hazardous. There's a lot of variations too. Like chemists have actually taken this molecule and changed that R group and made a whole bunch of different variations of this molecule, which we called pyrethroids. And these are used as synthetic pesticides. They're tuned to try to make them more toxic to insects and less toxic to people. And so you can do that. You can take a molecular structure, and you can change little bits and see what effect it has on its ability to, you know, do the job you want it to do. Plants do that too, but plants do it the slow way. They do it by evolution. And there's an accident that accidentally changes the structure, and it's either good or bad. And so through the process of many, many generations, plants develop new weapons, new molecules like this. We can do that quickly in a lab and screen thousands of different variations very quickly. What natural pesticide comes from the chrysanthemum flower? This one is pyrethrin. Sulfur, it's kind of the right color for sulfur, isn't it? Bright yellow, but yeah. So synthetic pesticides started to come along, and you know, kind of with the theme of the course, it was pretty relatively recent before people even considered environmental effects of anything that we do as humans. I'd say probably the 1960s is when this whole awareness kind of began. And 1874, a molecule called DDT, which has this structure, was first made. But it wasn't until 1939 that it was discovered that it actually worked very, very well to kill insects, and in particular mosquitoes. And mosquitoes, you know, we find them annoying, but they were much worse than annoying. They're great vectors for disease, particularly some really nasty ones like malaria. And so people saw DDT as a potent weapon against these insects, and especially beginning in World War II, when, for example, like US troops would be traveling to different parts of the world, certainly parts of the world that had lots of malaria. And in the US, actually, malaria used to be a major problem in the southern states. So this chemical was made. You could buy it anywhere in cans like this. People used it very liberally. They had these cans, and they'd spray people to kill biting insects, fleas, anything. DDT actually is not that toxic. We kind of talk about DDT like it's this like brutal chemical. It's actually like, you know, in the middle range, like many chemicals, synthetic or otherwise. It can be dangerous, but it's not like super toxic. 1948, the Nobel Prize in Chemistry went to this guy, Paul Mueller, for his discovery that DDT actually worked really well to kill insects. Okay. This was shortly after World War II, where it arguably saved a lot of people from developing disease. So this is one of my favorite limericks about DDT. It says DEET. DEET is not the same thing as DDT, Ryan. We'll talk about DEET a little later, maybe. A mosquito was heard to complain that a chemist had poisoned his brain. The cause of his sorrow was para-dichloro-diphenyl-trichloroethane. So that chemical name is the chemical name for DDT. Has this structure, and it's the para-dichloro. The dichloro refers to these two chlorines, which are what we say para, meaning opposite ends of the ring. Diphenyl, these things are phenols, so that's the diphenyl. Trichloro, and then ethane is that piece. So the name actually kind of tells you piece by piece what the molecular structure of this molecule is. US production of DDT started ramping up starting in 1939, but it started to really hit industrial levels towards the end of World War II, and you see it climbed and climbed and climbed up until the early 1960s. Then it started to drop, and now we don't see it anymore. It's been banned. So this is a chemical that you actually never see anymore. This is a map of, well, a plot of malaria incidents in the United States, and this is a log scale, meaning every time you go down one log unit, you drop the incidence of malaria by a factor of 10. So malaria used to be a fairly large problem. I believe this is number of cases per 100,000 people in the population. So about 100 people per 100,000 Americans were getting malaria in the United States back in the 1930s, mostly in southern states where the vector, which is I think it's the tsetse fly, which is a type of mosquito, bred. And when, it's pretty level for a long time until the 1940s when people finally had industrial amounts of DDT. And what they started doing in the US was started these industrial-sized DDT spraying programs. And they knew that that wetlands were where the mosquitoes bred. And so they just took planes full of this stuff and just wide scale spread it from the plane into natural areas. And of course, this killed all kinds of mosquitoes. I'm sure it killed all kinds of insects and non-target organisms too. But they were literally putting tons and tons and tons of this material indiscriminately into the natural environment. It wasn't like they were even confining it to farmers' fields or anything like that. It was very effective. It actually ended up, through several stages of this program, eliminating malaria as a disease in the United States. And to this day, it's something you almost never hear about in the US. So there was a couple of problems with this program, though. It actually worked very, very well. The problem is that if you use any one pesticide against any one pest, that pest, it might kill their numbers, might kill 99% of them. But that 1% that it didn't kill, first of all, now has a huge environmental niche it can take advantage of. No competition between members of its own species. Oh, thank you. I got an update on the actual malaria vector. Anopheles mosquito. Anopheles. The tsetse fly is something, though, isn't it? I don't know what that is. What happened, though, is the surviving mosquitoes actually started to develop resistance to DDT. And this is something we see again and again, is antibiotic resistance. If you use one weapon again and again and again against an organism, especially one that reproduces very rapidly, they can quickly evolve resistance to it. And so by the late 1960s, drug resistance was starting to grow in these bacteria. Not bacteria, flies, mosquitoes. And it wasn't just the US. I mean, in Canada, we didn't spray DDT because we didn't have any of that mosquito. But other parts of the world, like Madagascar was a country where they were getting like 1 million cases of malaria every year. And it's a relatively small area, and they started spraying DDT indiscriminately there too. And they actually brought their number of average cases of DDT to fewer than 10 a year. And since they discontinued their spraying programs back in the 1960s, they're back up to 1 million cases a year. So like, there was a real and like visible public health benefit to these spraying programs. Problem though, you know, it's foolish, I think, to do something on that scale and assume it's not going to have any downstream effects. Thing about DDT is the molecular structure, if I come back here, it's a very non-polar molecule. Doesn't have any OHs, no NHs. That means it doesn't hydrogen bond. That means it doesn't like to dissolve in water. So it ends up in the environment, and what it does is it looks for non-polar environment to be in. And one of the best non-polar environments out in nature is in the fatty tissues of animals or membranes of plants and animals. And so what happens is this process called biomagnification of chemicals like DDT that are very non-polar in the environment, where they might be present, they might like, you know, go into the membranes or fatty structures of single-celled organisms in water. But then those get eaten by something else, and those get eaten by something else. And what's happening is the top predators are eating a lot. You know, it gets concentrated in greater and greater and greater amounts, this DDT, the higher up the food chain that you get. So we happen to be up here, right? Not that we're eating eagles, but you know what I mean. We're like at the top of the food chain. We'll eat almost anything all the way down. And so that means that the predators that are at the top of this biomagnification pyramid are getting really high concentrations of DDT. So that's one problem, is that its non-polar shape or structure causes it to biomagnify. The other problem with it is that it's just super persistent in the environment. We saw the same problem with the chlorinated gases that were used in our ozone chapter. Right? Chlorine on molecules tends to make them actually pretty stable a lot of the time. So people, when they were spraying them in the 1930s, 40s, 50s, 60s, didn't care too much. In fact, if they stayed in the environment a long time, they may have viewed that as good because there'd be like a residual benefit. But they didn't think about this. So 1962, this is a very landmark development. There was a book that was published called Silent Spring by Rachel Carson. And in this book, what she did is sort of laid out her thesis that it was DDT spraying that was leading to like serious declines in populations of top predators, mainly birds of prey. And the whole idea behind Silent Spring is this idea that we're killing off our birds with these chemicals, and the idea is that sometime spring could come and you wouldn't hear birds anymore because we killed them all. It's kind of the idea behind this. And I mean, this was definitely a landmark book for like identifying this particular issue with this particular substance, but it was also kind of one of the first environmental books that captured the public's attention and got average citizens concerned and worried about environmental impacts of things that we're doing. So, you know, this was a pretty important piece just for how it caused public attitudes to shift around environmental issues. So Rachel Carson is very often sort of credited with kind of being the founder of the modern environmental movement because of this publication. In particular, she was looking at peregrine falcons, which are a type of bird of prey. And what was being noticed is that the bird eggs, the way DDT was affecting the birds is they were laying eggs, and their eggs had thinner than normal shells. And that meant when the bird went to sit on the eggs to incubate them, a lot of the time they were just crushing the eggs, and that would, of course, kill the developing fledgling, I guess you call it. Fledgling, no. That's a bird that's like learning to fly, isn't it? Embryo? No. Fetus? I don't know what you call a bird that's in the egg developing. But anyway, they believed it was DDT present in the blood of the animal that was responsible for this. And what they did is they actually found a whole bunch of peregrine falcon eggs, and they could tell the age of the eggs based on from the year they were collected from. And they tested the thickness of the eggshell, just like a little caliper, measure the thickness of each egg. And they plotted it versus the year that it was collected. And you can basically see like there's obviously some variation between here and here in the thickness of the eggshell. And that's probably in units of millimeters. Then starting in the mid-1940s, you can see how the thickness basically like jumped down. A significant amount. Like all of a sudden they're like 40% thinner. And that year it shifts corresponds with the beginning of those wide-scale DDT spraying programs in the US. So this was a pretty big smoking gun. Obviously, if they can't carry the eggs to maturity, that's going to cause big declines in the numbers. Bald eagles were another one. They're obviously a bird of prey, and in the US, a little more emblematic too, since it's sort of like the national bird and symbol of freedom and the whole thing in the United States. Bald eagle populations were like super, super threatened if you go back to the 1960s. What they do in the US is every state carries out a bird count where people go out and they count number of individuals, and they use some extrapolations and so on to get total bird populations. And they add them all together for all the states. And in 1963, there was 487 pairs of bald eagles in the United States, in the lower 48 states. That's a pretty small number. I wouldn't be surprised if there's that many pairs in the Annapolis Valley right now, right? Spread over the entire country, where this is the national bird of that country. Now, these years, they didn't have counts for every single year, or there's years where certain important states didn't participate, so they couldn't come up with a sum. But what you can see is starting from the early 80s, it's about doubled in population from the 1980s. And you can see it started to grow up to here. This is the number from 2006. And I think since 2006, they stopped bothering counting because they consider this species like saved. And they had a whole bunch of programs aimed at bringing the birds back, strict laws about shooting the birds. They believe actually that Nova Scotia played an important role in kind of creating a safe refuge for these birds to grow and then spread back down. And there was programs here where a lot of chicken farmers would feed the birds with dead chickens or whatever to keep the populations going. And you can actually see lots of bald eagles here in the Annapolis Valley. What about us, though? We are top predators, too. It was in the birds' eggs. Of course, humans don't lay eggs and sit on them, so I mean, we're not going to have that exact same issue. But what about DDT in our blood? And what about now, given that DDT is persistent in the environment and can last decades? Well, they have blood samples going back many, many years, and they took sort of stored or banked blood samples and checked for DDT concentrations in humans. And you can see there's 0 in 1942 before it was widespread use. Then it starts to grow and starts to grow. It peaks in the early 1960s, still about the same by 1968. Then starting in 1970, the levels start to drop back down. I don't know if it's down to 0 yet or not, but it's probably pretty close to 0. 1978 was a long time ago, right? That's what, 43 years ago? So effectively, we fixed the DDT problem, I guess. Of course, we now have a malaria problem, but, can't win them all. Remember we talked about malaria, the Chinese chemist Tu Youyou, who developed artemisinin, I think is the name of the drug. So we have weapons. So So here's a question. What book is considered to have been an important trigger for the environmental movement? Silent Spring. What environmental problem is associated with DDT? And this was decline of predatory bird populations, which of course, you know, you take out that important part of the food chain and the whole ecosystem changes. This is a picture of them just spraying DDT on a street just to kill bugs. Why not? It actually was like, the good thing about DDT is actually it was very toxic to insects, but very relatively non-toxic to human beings. Like the difference in toxicity to insects to humans was really huge. Oh, so by the way, the reason why these have gone down so much is they banned DDT. I think it was banned outright in 1972, and they started scaling back in the late 1960s. And so that's why you don't see DDT anymore. Problem was identified by Rachel Carson. Political action took place, and DDT has been banned. And its effectiveness was already starting to wane because the DDT-resistant mosquitoes were reproducing and multiplying. Okay, the next one I wanted to talk about was Agent Orange. And this is a chemical that was used a lot in the 1970s. It was used as a defoliant, which means it's used to kill plants, any plant. And it was used a lot in the Vietnam War by the Americans. And what they were doing is spraying forest cover to kill forests off so that guerrilla fighters couldn't hide in the forest. They're also using it to kill crops. So the goal there for the US Army was to drive rural people into cities, which would create social problems in the cities and cut off food supply for people. They wanted people concentrated. They didn't want them dispersed all through the countryside. So this was part of their effort. Agent Orange was made by a company called Monsanto that you might have heard of before. Monsanto was purchased a few years ago by Bayer Chemicals. So I don't know if you hear the name Monsanto anymore, but it was a notorious chemical company for many years. And Agent Orange is a 50-50 mix of two chemicals called 2,4-D and 2,4,5-T, which are chemical names for them. I have the structures coming up. And they created like thousands and thousands of tons of this stuff, and they shipped them in these big barrels. And I don't know how many million liters of this spray they ended up spraying in Vietnam over these years, but it was like a lot, you know? And these are all waiting to be shipped, to be sprayed in Vietnam. This is a map of Vietnam, and all the red areas are regions that were heavily sprayed, which, you know, most of the country was heavily sprayed with DDT, which, of course, killed the plants, which is the purpose. It had other problems, too, which we'll talk about. These two chemicals are very similar in structure. 2,4-D and 2,4,5-T, they have essentially the same structure, except if you look at the structure here, we have 1. The carbon with the oxygen is always counted as carbon 1, 2, 3, 4. So this has a chlorine on carbon 2 and carbon 4, and that's dichloro for 2-chlorine, so that's 2,4-D. It's dichloro on carbons 2 and 4. The other version is 1, 2, 3, no, you count the other way around. No, that's right. 2, 3, 4, 5, 6. So this is 2,4,5-T, T for trichloro. Okay. So these two would go in there, they'd spray it, and it's actually like they're actually very effective and relatively harmless compounds to use for this particular purpose. But this is the problem. If you take 2,4,5-T and you take 2 of them and heat them, they make this molecule TCDD, which you might remember from a few lectures ago as the most toxic known compound made by human beings. 1,000 times less toxic than botulism toxin, but still extremely toxic. Also, it's a chlorinated organic molecule, means it's stable in the environment, it's persistent, it's non-polar, so it does the biomagnification thing like DDT. And this was present in the Agent Orange as a contaminant, by like 1 or 2%. And it was known when it was manufactured that this was an extremely dangerous and toxic and carcinogenic, and anything bad you can say about this molecule it had. And Monsanto produced all of this, and they told the US Army, like, should let you know, we have this like extremely brutal substance that's mixed in with this, and just like give us some more time, we'll figure out how to get rid of it. And they're like, no, we just need it now. We don't care. We want the compound, we're gonna use it, and who cares? And so they ended up spraying huge, huge, huge amounts of this in Vietnam, along with the major components of Agent Orange, which are those pesticides. It caused like untold death and damage for years, and probably still. It's still probably in the environment. It's probably still, working its way up the food chain and still being consumed by human beings there and causing a whole bunch of negative health effects. There's a story in Canada too. Apparently in the early days of this, they did some Agent Orange testing just outside of Gagetown. And apparently there's a whole bunch of people, Canadians, that have been exposed to Agent Orange as well, along with the TCDD, the main contaminant, which can cause all sorts of health issues too. I think there was a payout just a couple of years ago by the federal government for people who were exposed to this. And I think there might be still concerns that there's a whole bunch of those barrels stored somewhere there, but I'm not sure. I'd like to see the news on that. 2,4-D, that was like one of the two components of Agent Orange. You can buy that still. Like you can go to Canadian Tire and buy a container of this. It's called Kill-X, or there's other versions as well. It's a selective weed killer, meaning it doesn't kill every plant. It only kills broadleaf weeds in lawns, typically is what it's used for. And when we say it's, a broadleaf, what we mean is plants are kind of like broken. I'm not a botanist here, but I might have this not completely right. But plants are kind of broken into two types. There's monocots and dicots. Dicots have leaves where there's a central vein, and then there's branches that come off. So think like trees, the regular leaf has a central vein with leaves coming off. And monocots have several veins that all run parallel, like grass. So this chemical, 2,4-D, will kill the broadleaf ones, but it doesn't kill the grassy type things, which makes it good for something like corn, because corn's a grassy plant. You can spray it, and it'll kill all the weeds except the corn. Or you can spray it on your lawn, and it doesn't hurt the grass, but it'll hurt everything else in there. So I guess you could buy 50% of Agent Orange. It doesn't have the dioxin, which is the really bad part, but, there you go. There's some concern with this chemical that use of it can increase your risk of certain types of cancers. And if someone uses it, often they put up these little signs to let people know. I'd say the concern is like if you sprayed your lawn with this and you have small kids playing out in the grass, or if you have animals like dogs running through the grass, I would say that would be a possible risk. There is some evidence linking it to cancer, but the evidence is really weak. I would say like it's hard to establish whether it can increase your risks of certain types of cancer or not. The jury is still out maybe on this compound. If you want my personal view on this particular substance, I would say, every chemical that you use has a risk and a benefit, and you have to weigh one against the other, the possible risk against the possible benefit. I would say for something like 2,4-D, the benefit of having a greener lawn with less weeds is extremely minimal. That's my own personal philosophy on that, though, and you can look at my lawn and see I practice what I preach. So I would say here the risk probably outweighs the benefit you're going to see. It's different, though, if you're using a pesticide in agriculture to maintain a stable food supply, or feed your family, or these sorts of things. So it's not always so black and white, like pesticides are bad, organic is good. Well, organic uses pesticides too, as we know, but anyway. So yeah, you can use this if you, depending, like I guess like a golf courses probably use a lot of this stuff. But maybe for them, like, I don't know, I guess it's part of it. Like, they have a big economic cost if the greens are in bad shape. What does Health Canada say about 2,4-D? It's concluded its reevaluation back in 2008, and it says 2,4-D meets Canada's strict health and safety standards, and as such can continue to be sold and used in Canada. So like, they got their eye on this. This may evolve over time, who knows? But that's my take. In terms of acute toxicity, it's moderately hazardous, so like, don't buy Killex and drink it, right? But the risk of poisoning yourself with an overdose through normal use is probably pretty low with this. Yeah. What war did the US engage in a heavy Agent Orange spraying program? That was the Vietnam War. The War of 1812. What highly toxic compound was found as a contaminant in Agent Orange and responsible for the majority of the health problems? This guy, TCDD, tetrachloroparadioxin. What commonly used broadleaf herbicide is a component of Agent Orange? That would be 2,4-D. This one's also in there, but that's not commonly used anymore. I think that was the one that actually rapidly converts to dioxin. That's probably why they don't include it anymore, because the dioxin problem was associated with that one and not the 2,4-D one. The number one herbicide used in the market today is glyphosate is the name of the chemical. It is the number one herbicide in use in the US. It goes by the brand name Roundup. And it has this chemical structure. And in terms of all of the things we talked about that makes pesticides good and bad, glyphosate is about the best thing you could imagine for an herbicide of this type. First of all, it's very non-toxic to mammals and other animals. Second is it does not persist in the environment. It has a half-life of like a couple of weeks in the environment. And when it breaks down, it breaks into phosphate, which is a fertilizer, and then glycine, which is a natural amino acid. So you have two byproducts that are sort of beneficial, I guess, for the environment, you could argue. The other thing is this molecule has 3 OH groups and an NH. This makes it extremely water soluble, so it's easy to apply. You don't need a plane and spread it. It also doesn't biomagnify because it's not non-polar. The other thing is this actually binds very tightly to minerals in the soil. So if you spray it on soil, like plants, it actually doesn't leach through soils because it grabs on to little particles and then breaks down over a couple of weeks. So when they developed this, it turns out it's very, very effective if it's absorbed by the leaves of plants, but it actually doesn't hurt them based on their roots. So what they can actually do is spray a field and then like basically wait a couple days and reseed, and the seeds will grow up just fine. So it can be used very easily with agriculture. And so this is why it's the number one herbicide. It's got like everything going for it that you could want in a pesticide. It was made by Monsanto too. And Monsanto's got a bit of a black mark against them, right? They got a bit of a bad reputation for developing things like Agent Orange just a few decades earlier. Roundup really started to come into its own in the 1990s when it really started to scale up in use. And the other thing Monsanto is really known for lately is genetically modified foods. So genetic modification also started pretty well in the 1990s. And one of the first things they realized was, you know, Monsanto makes Roundup, and they're like, we have like the world's best herbicide. We're also starting to dabble in GM foods. What if we made a GM food that actually fits with our other product? So they made what are called Roundup Ready crops that you could spray the entire field, And those crops have genetic enhancement to be immune to the effects of Roundup. And then this actually caught on. It's not only caught on, it's like 98% of the Roundup ready crops they make up 98% of the amount grown in North America. So there's people who, especially in the early days, came out against genetically modified foods just because there's this belief that the science isn't settled and all of this sort of thing. That has, I'd say, largely quieted down. You still hear some, but there's been many, many studies now over 3 decades that always come up showing that GM foods are safe and beneficial and this and this and this and this. But I guess there's an argument to be made that, genetically modifying a food to make it convenient to grow, I mean, I guess that's important too, because that's part of a stable food supply. But for whatever reason, Monsanto has been vilified by many for some things which are like truly nasty, like Agent Orange, and then other things which were maybe arguably a good thing. And if you go on like Netflix, there's all these anti-Monsanto documentaries that people make, and a lot of alarm around this particular company. But it got bought out, right? It got bought out by Bayer. So I don't know if they dropped the name, probably should have, just from the negative press that they seem to get. Look, and they call them, toxic chemicals. So, I mean, they're toxic to plants, but they're not toxic to people. In fact, they're way less toxic than any of those organic ones we looked at. It's slightly hazardous. It's one of the least toxic known pesticides that are in common use. So as a product, it's one of the safest ones that you can actually get. So the glyphosate hazard, there's basically zero risk of you poisoning yourself with it, but we also know that chemicals can also carry a cumulative effect, a chronic potential effect, and not surprisingly, that's been studied for this as well. On rats, they've discovered that the no observed adverse effect limit in rats was 31 milligrams per kilograms body weight. Divide that by 100, factor of safety, to develop the acceptable daily intake for humans, and we end up with this number, 0.3 milligrams per kilogram body weight. So that means if you weigh 60 kilograms, 132 pounds, 18 milligrams is what you can intake a day and be within the 100-fold safety margin for, going about your life. So what does that even mean? How easy is it to get 18 milligrams of glyphosate? And that's been studied. There's a paper which I think is linked in the info for these slides. There was a study where they actually looked at worst case scenario. Worst case scenario means that you eat all kinds of vegetables that are exclusively grown in fields that were sprayed with glyphosate, and you picked all the types of vegetables and fruits that keep the greatest concentrations in the final food that gets eaten. Because some plants pick up more of it than others. And it turns out the realistic worst case dietary intake scenario, if you ate all of the foods that are richest in it, in glyphosate contamination, you can get about 0.6 milligrams per day per person. Now, you can get a lot higher than that if you're a farmer and you're breathing it in or whatever. If you're using it at home, you're not careful with it. But if you use it carefully and sparingly, it can be actually an extremely effective substance and essentially risk-free. But there's no shortage of websites like Mercola.com, and what this website says is Monsanto's Roundup herbicide may be most important factor in the development of autism and other chronic disease. And this was actually a fascinating rabbit hole to go down, where this article has come from. And Mercola.com is, by the way, very well known for putting all of these kinds of articles linking chemicals to bad outcomes. And Yes, of course, there's a shop on that website, and it's, you know, we talked about these sorts of sites before. What it comes from is this paper that was published in 2013 by a doctor, Stephanie Seneff, and she was a prof at MIT, and her specialty was artificial intelligence and computer science. So she's not an epidemiologist or, you know, somebody who would have sort of a scientific background in this field, but she had a faculty position, which gives her, I guess, some degree of you know, credibility. This journal, Entropy, by the way, I never heard of it before, but note here, there's a note added by the publisher. The editors of the journal have been alerted to concerns over bias in opinions and bias in the choice of citation. The authors stand by the content as published. So they put out this expression of concern. They said, we're not going to delete the paper, retract it, but we just want to warn people that this might be a skewed kind of opinion piece. And what it does is trying to draw a link between the use of glyphosate and the gut microbiome, and then that causing modern diseases. And this isn't based on like experimental study. This is based on like making correlations with different things that she's seen in terms of trends over time. And if you go to her website, you can actually download her presentation slides and see what this data looks like. And this is it. This is the rates of autism in blue, diagnosed rates of autism in the US from 1995 up to 2011. And you can see it's increased a lot. And the red is the use of glyphosate. And what she says is these are correlated really, really well. There's a correlation coefficient of 0.9972. Therefore, she says, it's our increase in the use of glyphosate that is causing autism. What elementary mistake has she made? She's confused causation and correlation. Just because two things are correlated doesn't mean one's causing the other. So the first argument actually against this is actually a lot of people believe the rates of autism have not increased at all. Just the rates of diagnosis of autism have increased because of, you know, clearer diagnosis criteria and awareness and this sort of thing. It's sort of like, the quote I heard is like, you know, Pluto was only discovered in like 1939, but I'm pretty sure it was there the whole time. Whatever year Pluto was discovered, I don't know. So, you know, probably that rise in blue isn't even real. But anyway, this is not based on a causative, this does not establish a causative effect. In fact, if you plot autism rates against organic food sales, you get almost the same correlation coefficient. And so, you know, I don't think either that autism is caused by eating organic foods. You could basically plot autism diagnosis against anything that's increased since the 1990s. Use of cell phones, that's increased since the 1990s. Total bandwidth of downloaded movies on Netflix or whatever, like almost anything that you could, that has risen will correlate with autism. This is another one of her slides. She's looking at diagnosis as like a one in so many, and she makes the alarming prediction that by the year 1930, 50% of all children in the US will be autistic. And then I think it was 2048, 100% of children will be diagnosed with autism. And all she does is she takes like the current diagnosis curve and just extends it off into the future, which, you know, obviously is not, not going to work. All right. By the way, so there's no real scientific correlation, causative link between any chronic disease and the use of glyphosate. So what is one of the positive attributes? Weeds cannot develop resistance to it over time. That's actually one of the problems with Roundup is weeds are developing resistance to it. Like everything that we use in huge amounts, it doesn't work forever. This is a good thing. It does not persist in the soil. It does bind strongly to minerals. It does have low toxicity to humans and other mammals. It is water soluble, making it easy to distribute, and also prevents it from bioaccumulating. But this is sort of the negative of it, which, it's like antibiotics. Use them while you got them. Sooner or later, they're going to stop working. Dr. Stephanie Seneff has incorrectly implicated glyphosate with what condition? And that was autism. Although I wouldn't be surprised if there's a bunch of other ones in there as well. That, yeah. One other thing I just wanted to say about Roundup. There was an important court case a couple of years ago where there was a groundskeeper, I think in California, who used glyphosate all the time. It was like part of his job. He was like spraying weeds, and he developed cancer, and he sued Monsanto, or Bayer, for causing his cancer. And he got awarded like this huge settlement. I don't know what it was, $80 million or something like that. Because the court concluded that it was likely his use of this compound that caused his cancer. Which was sort of bizarre, because like how can a court of law determine something like that? And I think it ended up getting overturned anyway. But I don't know. I don't know where that landed, that particular court case. I think it was in the news when Monsanto got bought out by Bayer, so Bayer just sort of adopted that problem. Nicotine is the next thing I want to talk about. Nicotine is a natural insecticide produced by the tobacco plant, and it's used by the tobacco plant so bugs don't eat it. It's an insecticide, and it actually is a very effective insecticide, and it has this relatively simple structure you see here. So of course, the main compound in cigarette smoke that causes people to feel what they feel. This is one of the few pesticides that's in the highly hazardous group. It's actually extremely toxic in small amounts, so you could easily, I guess, potentially overdose on this if you were exposed to large amounts of it. But because it's extracted from plants, it's considered natural and therefore allowable in organic farming. What chemists have done is taken nicotine and monkeyed around with its structure to come up with better versions, ones that are less toxic to humans and more toxic to insects. And they had this whole class of synthetic pesticides now that are known as neonicotinoids. Neo is new, and then nicotinoids means that they're like nicotine. So they're based on the structure of nicotine. So if you look at the LD50 for nicotine with mice, 3 milligrams, very low concentration to hit your LD50. It's about like, what, 150 times less toxic, in this case in dogs, but 150 times less toxic when you look at this compound, imidacloprid, which is the #1 neonicotinoid pesticide that's used today. These are for, Roundup is used for weeds. This is used for bugs. Okay. It's way more deadly, though, to insects. We said 450 milligrams per kilogram body weight for dogs, 230 micrograms per kilogram. There's 1,000 micrograms in 1 milligram. So this is around 2,000 times more toxic to insects, like bees, than it is to dogs. So this is what people have been using to kill insects and protect crops. The issue is, though, that there are good insects and bad insects, and just broadly killing them all causes problems, especially because we rely on certain insects, like bees in particular, to do our pollinating for us. And so these neonicotinoids, are really implicated in very serious issues with bee populations in particularly in the US. So this is looking at something called colony collapse disorder. This is looking at the percentage of bee colonies lost each winter in the US. See, it hovers somewhere around 25 to 30%, which is a pretty significant, number to lose each year. And it's risen sort of from earlier times. And it's believed that this is, at least in part, due to the use of neonicotinoids. This is a complex issue, though. It's not just neonics. It's other things, too. There's like mites that have sort of proliferated in bee colonies that are believed to be responsible for part of the problem. And it is a kind of a complex issue, and you can't really point necessarily to any one cause. But these neonicotinoids are certainly under the gun. So the David Suzuki Foundation, for example, has a campaign against neonicotinoid use in Canada, saying that Europe banned them back in 2018. Canada needs to pick up the pace to protect bee biodiversity. So again, I feel like DDT in the early days, it was discovered to be useful. It was used widely. And then eventually, when the science kind of got settled and they realized its negative effects were worse than the positives, it got banned. I feel like with neonicotinoids, we're like in the early phases of that. And it could go either way. We could end up using them, or insects could develop a resistance to them, or we find that they're worse than their benefits and we just stop using them altogether. So, at the end of the day, are pesticides safe? And it's a complex question. I'll say this, if we didn't use any pesticides at all, our food supply would plummet and billions of people would starve. So we need them, but we need to be judicious. I don't think we all need green, weed-free lawns, right? So I think there's certain uses of pesticides that are unnecessary, probably. I also am not a fan of the use of like DDT, where you drop tons of it from a plane broadly into the environment. I think that is irresponsible to do that sort of indiscriminate use. I think any use that we do use on crops and in the environment, first of all, needs to be very carefully studied and examined, what the potential effects are on the environment, on human health, and all the other things in between. But do I think we should get rid of them all? Absolutely not, right? Because we just simply need it to grow the food that we have. We can't go back to how we did things 100 years ago and maintain a world population of what we have right now. It's just not possible. So really, like, advances in chemistry have made it possible for our population to have ballooned to what it is right now. Yeah? So that's an interesting question. Will pesticides become more concentrated as insects develop immunity to it? So I guess there's one strategy. If the insects start to become immune to it, you just use more pesticide. I think that's a short-lived solution. The chemist's solution to something like that is take this molecule, well, let's change the Cl to something different. And maybe now it works just as well, but the insect doesn't know how to handle it. This is how we've done it with antibiotics. Like penicillin is a very common antibiotic, but there's hundreds of variations of penicillin that we've gone through. So like amoxicillin and cloxacillin and ampicillin, they're all like slight variations of penicillin with the goal of either increasing its stability, increasing its potency, decreasing its negative side effects, or just getting around defenses that organisms have developed against it. So I would say the nice thing about chemistry, there's an infinite number of variations of this compound, and you can continue to play with it, and that's what people, I think, are spending a lot of time doing. So the growth of resistance against things like this, I guess, is good for me because it always keeps chemists in business, right? So there's positives for some of us. But there's other kinds of chemists too, right? Like there's some chemists whose job it is to measure how much of this there is in the environment or how much there is in the blood. Analytical chemists to like learn that part of it. And they work together with biologists and biochemists, and lots of people have to work together to really develop a clear picture of these types of issues, which are really wide scale. Cool. I think we're done, actually. Oh, we got a question. What common insecticide has been recently associated with colony collapse disorder in honeybees? That was B. The other ones would do it too, but we don't really use them on high levels. That's it. Look at that. 4 minutes left, and we're at the end of the course. So thanks, everybody. And keep eyes open for my emails, which will be plentiful probably in the next week or so. I look forward to seeing everybody's presentation, hopefully by end of today. And that's it. Great. Ooh, I removed my background.